Alright guys, today's goal: the learner will master the understanding of exponential growth and decay. An exponential function has the form y equals a times b to the x, where a cannot be 0, and the base b is a positive number other than 1. If a is greater than 0 and b is greater than 1, then the function y equals a times b to the x is exponential growth function. And b is called the growth factor. The simplest type of exponential growth has the form y equals b to the x. That's when a is 1. So here's the standard function. Notice how it gets closer and closer and closer, but it will never equal 0, because a positive number to an exponent never equals 0. Okay? So the x-axis is the asymptote of the graph, and the asymptote is the line of the graph approaches more and more closely. And as it moves from left to right, it rises. That's why it's called growth. As you move to the right, it gets bigger. So you have studied exponential growth functions. In this lesson, you will study exponential decay functions, which have the form a times b to the x, where a is greater than 0, but b is between 0 and 1. Notice it's not negative still. Both a and b are still positive. Okay? So the base b of exponential k is called the decay factor. Okay? The parent function is still b to the x, but again, b is between 0 and 1. And notice how instead of getting bigger, as you move left to right, it gets smaller, but it still approaches 0. Okay? Alright. So the horizontal asymptote for both of these, y equals 0. Alright, so it says graph y equals a times b to the x minus h plus k. It's the same h, same k, same a. So here, a is 1 because it's just 3. B is 3. H is 1. K is 2. So if I start by graphing this, let's say I do negative 2, 0, and 2, and that's for y equals 3 to the x. I get 3 to the negative 2, which would be 1/9. 3 to the 0, which is 1. 3 squared, which is 9. Okay? So if I go to graph those, negative 2, 1/9, so it's going to be just above 0, 1, 2, 9. Oh, missed that a little. So that's what it would be. Now there's two different ways. You could just pick the same two numbers, or same three numbers for that for the next one, or think about the shifts that are going on here. So I started with this. That positive 1 means move to right 1, so add 1 to all these. So I would get negative 1, 1, 3. Plus 2 means add 2, add 2, add 2. So I would get 2 and 1/9, 3 and 11. So negative 1, 2 and 1/9, and then 1, 3, and 3, 11. And see that plus 2 means put that horizontal asymptote at 2 instead of 0. Okay? Or you could have just done still -2, 0, and 2. And you would have gotten 1/27th, 1/3, 3. And it'd still be the same graph. Okay? Oh, wait. Hold on. I added those wrong. This would be 2 and 1/27th, 2 and 1/9. Nope, 2 and 1/3. And then 5. Okay? Same graph, though. State the domain and range. The domain, all real numbers, negative infinity to positive infinity, because there's no x value. I can't plug in the range. We're talking for this one. What does it have to stay above? 2. So it's 2 to positive infinity. For this one, the domain is still negative to positive. It will always be negative to positive infinity for exponential growth. The range is 0 to infinity. Okay? So there's exponential growth. Here's decay. Because see how b is 2/3? Isn't that a number that's between 0 and 1? So if we do the 2/3 to the x first, if I plug in -2, you would get 9/4, because 2/3 to the -2 means 3/2 squared, which is 9/4. Plug in 0, you get 1. Plug in 2, you get 4/9. So if I graph that, that's just the easy point to graph, and then -2 and 9/4, which is 2 1/4, so just above 2. And then 2 and 4/9 is just below half. So it's going to look like that. Then the only shift was left 1. So what you can do is instead of add 1, you can say -1, -1, -1. So -3, -1, 1, and then these don't change. So we go -3, -1, 1. Okay. So there's the decay ones. Alright, exponential growth models. When a real life quantity increases by a fixed percent each year or other time period, the amount of y of the quantity after t years can be modeled 1 plus r to the t. R is the growth, 1 plus r is the growth factor, r is the rate of growth. So see here it says, in an exponential growth model, y equals 527 times 1.3 to the x. Identify the initial amount. Well, A is the initial amount. So initial amount is $527. Identify the growth factor. Well, 1 plus r is the growth factor. So the growth factor is 1.39. And the percent increase, well, you do 1.39 minus 1, 0.39. So your rate is 0.39, which would be 39%. So let's say I said, find me the amount of money after 5 years. You would say, so 527 times 1.39 to the fifth, $2,734.54. Okay? Exponential decay models. So instead of growth, if it's decaying at the same rate, 1 minus r is the decay factor, r is the rate of decay. It says the value of a snowmobile has been decreasing by 7% each year. After 3 years, the value is $3,000. Find the original cost. So that means we're looking for A, because that's the original. So you say 3,000 equals A times 1 minus 7%. Now remember, convert that to a decimal though. So move it 2. So 0.07 to the third power. So you get 3,000 equals A times 0.97 to the third. Or 0.93. 0.93. So divide by that. So you would get A equals $3,729.68. So that's what you paid originally. When you try to sell it 3 years later, you've lost $729.68. So that's, if it's a growth factor, you add the rate. If it's a decay factor, you subtract the rate. There's another type of growth that we need to talk about. It's called compound interest. Okay? It says, exponential growth functions are used in real-life situations involving compound interest. Compound interest is interest paid on the initial investment called the principal. That's the P. And previously earned interest paid on only the principal is called the simple interest. Okay? It said consider an initial principal P deposited in an account at an annual rate. Annual means yearly. Compounded n times per year. The amount A in the account after 2 years is given by this equation. So it says you deposit $2,000 into an account that earns 4% annual interest. Find the balance after 3 years if the interest is compounded yearly. So the n is the number of times it's compounded over that time. So if this said, let's change that. Let's say instead of yearly, let's say monthly. So I would get A equals $2,000 principal, 1 plus 0.04 because it's decimal form. Now, if it's compounded monthly, how many months are in a year? Because it said annually. 12. And then the number of months that have gone by is 12 times 3. So just go ahead and plug that into your calculator now. And I hit something wrong because it told me $55.74. There's no way that it grew from $2,000 to $55. So let's try that again. See how if you think about your answer, you should know if you did it right or wrong. it was $2,254.54. Okay? If it said yearly, that n would only be 1. If it said daily, how many days are in a year? 365. If it said weekly, how many weeks are in a year? That's what you need to figure out. Okay? See you guys in class.